great pleasure to welcome today Colin Howson, who's a professor at the University of Toronto. Toronto got him from LSE in 2008, and it was a very good thing to have done. Colin's primary interests are in philosophy of science, logic, foundations of probability. He was formerly president of the British Society for Philosophy of Science, and he has a number of books that have been extremely influential. These include Hume's problem, Induction and the Justification of Belief, Logic with Trees, An Introduction to Symbolic Logic, and with Peter Urbach, he wrote a book that is a real classic, of canonical defense of Bayesian reasoning. So we're extremely pleased and honored to have him with us today. His title is, Should Probabilities Be Countably Additive? Welcome.
Well, thank you very much for inviting me here. Thank you, Charles. And thanks everybody else for coming along to this rather sort of distinguished environment I've got here, including looking around at the audience. If I can use the language of the King James Bible, there are several people here, the latchet of whose shoes I am unworthy to stoop down and unloose. And I hope that they'll be very tolerant. Anyway, thank you very much indeed. This is a sort of subtitle for the talk I'm going to give. I thought the main title, Should Probabilities Be Countably Additive, was a little on the sensational side. And so I thought I'd tone it down a bit. You've read the importance of being, or seen the importance of being earnest at one point. Miss Prism says to Cicely, you should go and do your political economy, that you may omit the chapter on the fall of the Repeers in somewhat sensational. Anyway, this is, I thought that was a bit sensational. So, anyway, another lottery paradox. So there will be references to two great analysts of lottery paradoxes, Henry Kaiberg and Bruno Definetti. Their paradoxes are very similar, and they have very similar resolutions. I'll give them yours by way of introduction, so assuming this gizmo works, let's go. Yeah, so it's about, should probabilities be countably additive? Now, what does countable additivity mean? It means that if you've got a countably infinite family, but countably just means a family that can be indexed 1-1 by the natural numbers exhaustively. So if you've got a countably infinite family of mutually exclusive possibilities, then the probability that an unspecified one of them occurs is the sum of the probabilities of each. And this sum is easily shown to exist and be well defined. So that's fine. And this is now going to be set against its competitor, finite additivity. So countable additivity is very prescriptive. It says that you have to have probabilities added over countable infinite families. Finite additivity is permissive. It says you can do that if you want to. The minimum that is required is that the probabilities be finitely additive, which in effect means that they simply add over pairs of disjoint events, because once you know that they add over pairs of disjoint events, then just by simple induction you can work out that they add over any finite family of disjoint events. Okay, so as I say, the important thing here is that one of these is very prescriptive, and the other one is very permissive. And to be in tune with the times, where of course we don't like over-prescriptive things, but we do like very permissive things, although I sense that's changing now a bit. This is a talk really in defence of number 2 on your programme, finite additivity, the permissive one. Okay, so what's the big deal here? What's involved in all this? Argument CA is just going to be countable additivity, FA is going to be finite additivity. There are sort of two main views, really, you look at the applications of formal probability theory, there are sort of two main, there are lots and lots of sub-varieties of these things, but in terms of work being done by most people, there are probably two main varieties. One is measure theory statistical, where the statisticians and the probabilists think that they're doing some sort of empirical work, but they use the measure theory apparatus that was invented for them at least specifically invented for probability by Colin Howson in a famous monograph published in about 1930. So I call this the measure theory statistical view. And B, subjectivism. Now, in particular, something called coherence-based subjectivism. There's subjective probability has a number of sources. One comes out of utility theory, and it uses a number of representation theorems. The other one, which is the more, as it were, user-friendly, definitely easier to understand, very flexible, is due originally to Bruno, the great Italian mathematician, economist, statistician called Bruno, and philosopher actually, great follower of Hume, Bruno Definetti. And it's based on this notion of coherence. I'll show you what that is in a minute. Anyway, let's just look at A briefly, because countable additivity is actually part of measure theory. A measure is just, by definition, countably additive. Well, mostly there are some sorts of measures, which for some reason or other I don't know where the terminology came from. There's now there's work that's been done for the last 50 years on finitely additive measures. It had a very bad press first of all, but in fact there's a lot of work now being done on finitely additive measures, which are called charges. And it's a very peculiar terminology, and I don't know where it comes from. So if anybody knows where the word a charge for a finitely additive probability comes from, I'd be very grateful if they could tell me afterwards. But mostly, measure theory, this measure theory approach is sort of really based on countable additivity. And it's said, if you look at the sort of standard text, you find all sorts of claims for explanatory power for this measure theory statistical approach. It's said to explain, now by explain with probability 1, all sorts of interesting things. It's said to explain the limits. There's always been sort of tantalizing limits between formal probability and relative frequencies. Ever since the serious subject got underway, people have been looking at this and trying to find some way of explaining exactly what this link was. And so now a lot of people think they know what the link is, because with probability 1, assuming countable additivity, assuming a rich enough language, you find that an infinite sequence of what are called IID events, independent, identically distributed events, that's to say, it's like flipping a coin. Each time you flip the coin, you've got exactly the same probability of heads, and the flips are independent. So this is the classic model of IID, called Bernoulli trials. And with probability 1, you can prove in this theory that in an infinite sequence of these things, the limit of the relative frequency, the relative frequencies do actually converge with probability 1 and are equal. That limit is equal to the common probability in at each trial. It will also explain with, so these are all with probability 1 explanations. So you've got this big sort of explanatory theory, also it said. So you explain all sorts of interesting things and things that, yeah, I see now, with probability 1. So, for example, another example of why a 1 will occur at least once in such a sequence of those things, why the average time the system spends in a measurable region R is proportional to the measure of R, and lots of things. Why, what are they called, martingales, bounded martingales converge to a all these things are explained with probability 1. So you have this marvellous, what looks to be a very, very powerful explanatory theory. Then there is some mathematical. The other great advantage of countable additivity is that it gives you a very simple, powerful mathematical theory. It guarantees that the probabilities of many types of limit events are uniquely determined. It guarantees that limiting operations are interchangeable. It guarantees that when you have a sort of distribution function of a random variable that contains all the information about the property distribution of the variable, and so on and so forth. It's supposed to be, everybody says this is just a really wonderful theory. It supports this thing called the Lebesgue integral, and so on. I don't spend too much time on this because to go into it would require more mathematical knowledge than I have, and it's not particularly relevant to what comes later, so let's just pass on. Oh yeah, another thing, countable additive. So this is this sort of alleged advantages of having a countable additive probability. The other thing is this thing called the sum condition. Countable additivity, unlike finite additivity, satisfies the intuition that the probability of a set of things must be equal to the sum of events, or a partition must be equal to the sum of the probabilities of its parts, at any rate where the notion of sum is meaningful. Because then you think, well what about these things like the real line, where you've got countable distributions that give zeros each? Well, yeah, there's no notion of sum that goes with that, so you can forget about that. What you do there, you have a surrogate, it's called density, and you can integrate densities, so forget about that. Where the notion of, as of a discrete sum is involved, the sum intuition is satisfied by CA, but not by FA. Then there's this property called conglomerability. Countable additivity guarantees, unlike finite additivity, that if you've got a countable partition of events, then the conditional probability of, and if the conditional probability of each of A conditional on each of these members of the partition lies in some interval, and so does the probability of A. Now, the intuition behind this is a very sort of plausible one. I mean, it's rather like saying, if I know that whatever, so here's a set of alternative possibilities, and if I know that whichever one of these possibilities happens, you will get this happening, then you will get this happening. It's a sort of version of this. This is equivalent to another property called disintegrability. I'm not going to talk too much about this because I can't pronounce it easily, and so I also avoid it's sort of a lot. So I even now have to be careful. Disintegrability. A probability is disintegrable along the margin if it can be written in that very familiar form, of course, which is used all the time. In an elementary probability, you will decompose an event along the margin in this sum. So that's all for good. That's guaranteed by countable additivity. Finite additivity guarantees you can do that for any finite sum. Countable additivity guarantees you can do it for any sum that's well-defined, sum over an infinite partition. How do we do? So far, so good. Countable additivity also guarantees, so it's a nice sort of, I just ended this list, then I'm going to come later on, so that you don't live in a state of awful suspense for too long. I'll say why I think that all this is actually very overplayed. Guarantees also that if you've got a random variable x, then there's a quantity called P of A given x, determined almost uniquely by the probability function P, even when the probability that this variable takes that value, little x, is 0. Now, all those who have any acquaintance at all with probability theory knows that usually there is a definition of conditional probability, which conditional probability of A given B is the probability of A and B divided by the probability of B. Well, of course, that only makes sense if the probability of B is non-zero. And if it's 0, it doesn't make sense. And so you think, well, okay, here's some sort of singularity where sort of funny, nothing happens there, basically. But in this, you actually have... Now, the thing about this is very interesting because you don't actually need a separate notion of conditional probability. It actually comes out. It supervenes on an unconditional probability. For those who know about such things, it is something called a Radon-Nikodym derivative. And you can show that it exists, and that when you write a P of A given x, which is to be read the probability of event A, given that x takes the value little x, and if you've got a set of x values B such that the probability B is actually greater than 0, then this agrees with the ordinary definition of conditional probability for where that set is the condition. So that all looks very nice too. So you seem to get a lot out of this. However, now we come to the, so what's against all this? Not so much what's against all this, but how, I mean, are these really serious claims for countable additivity? There are actually, I'm going to come on to talk about really serious claims against countable additivity a little later. But countable additivity has a very good press, and you will, most of what you read, if you read anything at all into sort of, sort of philosophical foundations of probability, most people say, oh, you really need countable additivity, you don't have it, it's all a mess, you can't do things, you can't, it's all horrible. Whereas with it, you can do all these nice things. So now let's look at the however line. The first thing is, what about these with probability 1 explanations? Because they sound all very nice, well, isn't that great? With probability 1, not just either one, actually one. You will get the identity between the common probability of the sequence, flip a coin, infinitely many flips, lo and behold, with probability 1, the probability of that coin landing your head once is the limit of the relative frequencies in those flips. That's really nice. Well, think about it a second, and suppose you don't know what probability means. So somebody says, well, with probability 1 you get x equals y. Suppose you've got two quantities, x and y. And someone said, look, this is a pretty good theory. With probability 1, you know that x equals y. So that explains why x equals y. Whenever you see x being equal to y, well, now you know why it happens. It's got probability 1. You think, aha. Well, what about saying x equals y with Pongo 1? What does that explain? Nothing. Come on. What does Pongo mean? Well, exactly. What does probability mean? There's no way you can say with probability 1, this happens is an explanation of why it happens until you give some sort of meaning to probability 1. But that way lies trouble. Because of all the attempts which have been made to give empirical meaning to a statistical probability, they will turn out to be very much more difficult than anybody thought. And I suppose the main one, the one that if you read, I'm a great reader of popular physics, on the grounds that I was removed from serious physics at a relatively early age, and often wondered what they did after I was removed from the class. Fascinating what's been going on, I can tell you. And a lot of these people also talk about these physicists who are now making fortunes writing these popular books. You and I, I'm sure everybody else in this room, is funding them in their old age. Guys at the Perimeter, Stephen Hawking, all these people. Well, occasionally they'll talk about probabilities. They all seem to have this view that probabilities, as used in physics, are limiting relative frequencies, or long-run relative frequencies. That's what they all say. Look at the two-slit experiment, what are the long-run relative frequency of what you get behind this split screen, this two-slit screen, and so on. So they all have this view that really empirical probability is just limiting relative frequency. Well, the trouble with that's fine. And in fact, you can prove, one of the nice things about taking this sort of hard-headed, no-nonsense approach, is that it's trivial to show that limiting relative frequencies obey, wait for it, the finite additive probability axioms. And they don't obey the countably additive probability axiom. Not in general. In general, there are cases where, and you can actually construct them, you can have, well, in fact, it's terribly easy to construct. Just think of a sequence in which a number occurs exactly once, and take it to infinity. And then what's the limit of the relative frequency of each number? 0, but each number's got to occur at least once, so the probability that one of them occurs is 1. So it's not countably additive. Is there also other, well, it's not going into that now, but anyway, so, but you can show that they satisfy the finite axiom. It's very easy, it's a simple mathematical exercise to show that they satisfy the finite additive axioms. So that sort of rather goes against this, this view. The mathematical considerations are largely about simplicity and convenience. And again, it begs the question. I mean, I can think of a simple and very powerful mathematics. I just identify everything with 0. So here's a physical quantity, I say, okay, it equals 0. Yeah, that's incredibly powerful and very simple. It doesn't get you very far, but it's very powerful and very simple. So power and simplicity have to be traded off against some sort of independent justification. So that sort of begs the question, I think. The sum intuition is not even satisfied by countable additivity because it's perfectly, I defer here to a member of the audience who is sitting looking at me right now in an orange jumper, that you can actually add an uncountable number of zeros by transfinite induction, you get 0. You have an ordinal function, which is the sum of the first, so it's basically all these, we'll order the real numbers, okay? Then just add the first n of them, and then add the first alpha of them. It's always going to be 0. So it doesn't satisfy sum. Countable additivity does not satisfy. It satisfies it for the countable case, it doesn't satisfy it for the uncountable case. Okay? Countably, I didn't go too far into this because I tried to write out a formula and unfortunately didn't get transferred properly to the screen, so I'm not. There are countably additive probabilities which are non-conglomerable. I started out by saying they're always conglomerable. They're conglomerable over countable margins, but they are, you can you can show that there are uncountable margins where they're not conglomerable. So that goes by law. So if you're going to rest everything on this conglomerability property, then it doesn't work either for countable additivity. So that's technical, let's not go into that. What about this conditional probability function? Well, this actually has some unfortunate properties. One of which, it can be what's called improper. You can have an event of property 0 such that the probability of A given A is 0. That turns out to be quite possible. And you can also have a situation where the probability, suppose you've got a random variable x and it takes the value little x, and it takes that little value little x on a set of property 0, then it's quite possible for the probability of A, given that x equals little x, and the probability of A that y equals little y to differ, even when x equals little x and y equals little y, determine exactly the same event. And yet, you can show these differ. In fact, there's a very famous example. To use Borel, what's called the Borel paradox. You assume, if you've got a sphere like the Earth's surface of a sphere, assume there's some uniform probability density on this, require the probability density of a point given that it lies on a great circle. Well, we choose coordinates such that either the circle is a meridian circle, goes through the poles of your coordinate system, or it's an equator. Then you show, using this, Colin Howson actually proved this in his famous monograph, that if you choose the great circle to be a meridian circle, then the probability of a latitude, the latitude taking any value, given that, where are we? Given a particular meridian circle, I was given a particular value of the longitude, that determines a particular meridian circle. So the probability that latitude lambda, it takes a particular value lambda, is actually proportional enough to the cosine of lambda. While if you assume your great circle is an equator, determined by latitude equals 0, then the probability of a point on the equator is actually uniform probability. When you think about that, that's very odd. Because originally, before you put the coordinates down, you just had a great circle. You were the one who determined whether it's going to be a meridian circle or an equator. But how you do this gives you different values. In one, you get a non-uniform probability, and the other, you get a uniform probability. Isn't that odd? And that's an example of what we just saw before. In fact, what you have here is you have a latitude, a given meridian circle is determined as the longitude tends to 0 around that. This is called a lune on the surface of the sphere. And when you take the limits, so you get the conditional probability, you get the proportionalities of the cosine of lambda. On the other hand, in the second case, you've got a band around, and when you let that band width tends to 0, you get the uniform probability, 1 over 2 pi. So it's not so good, is it? Where you can, and now Colin Howson, who actually talks about this, says, well, what you've got here is an interesting case, but what it means that you can't consider a conditional probability conditional on a single event. You can't say it's conditional on that event when it's got probability 0. It has to be a three-place relation. It's conditional on an event plus a particular way of limiting a limiting process that gets you to that event. So now it turns out, okay, you've got a notion of conditional, but now it turns out to be a three-place event, a three-place thing, which again is very contrary to intuition. So it's not clear that that either is a terribly great. And also, the other thing about this is that you can change the value. On a set of property 0, you can actually change the value, make it any value you like. Because these things are defined by an integral equation, and the integral has the same value, whatever particular, however you change a particular point. So it's not even, well, it's not even uniquely defined. It's almost uniquely defined. Almost uniquely hides a multitude of sins. Right, let's go on. Right, let's come now to the bit that I'm going to be talking most about, what Bayesians think. The Bayesians think about this. What's sort of mulling over this? Well, the trouble is, as I said, the most popular approach to subjective Bayesianism is founded on a notion of subjective probability. That notion of subjective probability, the most popular way of presenting it, probably still in terms of worldwide constituency, has more people than any other, is based on this notion of coherence, which is used in Definetti. It's very accessible and very understandable, as we'll see. Let us see. Well, there's something called vulgar Bayesianism. There's Bayesianism, so think of Marxism. Now, everybody, as soon as you start talking about Marxism, you've got these people called vulgar Marxists. They're people who don't really understand the details of what Marx actually said. So, when you're among real Marxists, they say, oh, no, that's a mistranslation. What Marx said was the following. He didn't say that. Everybody thinks he said that. But no, he said this. Anyway, so the vulgar Bayesianism is like vulgar Marxism. It's supposed, they all say it's Definetti, but we shall see about that. So, you've got a personal, if you're a Bayesian, what that means is you have a personal probability assignment. You assign probability to anything, you know. Any uncertain event, in this very simple model, we're talking models here, by the way, all the time we're talking models. One should never actually forget that, because it's very important. So, when you're, say, reading a book on deductive logic, as people do from time to time, it's a model. Nobody reasons deductively in that way. Nobody on Earth. We'd all die if they did. Nobody reasons like that. But it's a model. It's supposed to be a useful model. Classical deductive logic is a broad spectrum model, which is known to be hopeless for things like conditionals. And so you have to invent something else for that. And it's sort of okay mostly, but it's always a model. You know, two truth values. Just two truth values. Not really. Sharp truth values, no, not really. So it's a model. It's a very, very simple, crude model, but it does its job quite well. Bayesians, both the vulgar and the not so vulgar versions, also are a model like this. So when people say, well, no, that's not exactly, so we want to have a sort of Bayesianism of the human face or something like that, forget it. We're always dealing with these relatively crude models. You trade realism for simplicity, in a sense. Anyway, so let's look at what this is. So in this model, people have personal probabilities. It's the way they assign uncertainties, degrees of uncertainty to events, some set of propositions. Now, the way a personal probability assignment is called coherent, just in case, were you to bet, so the traditional view of your measures of uncertainty is that they're the fair odds that you put on various things. There's nice quotations from literature where people say, well, the odds on so-and-so are so-and-so, and the probabilities are just simply these odds normalised, so they don't go up to infinity, but they stay nicely down in the unit interval. So in a way, you're always thinking about bets. So personal probability assignment is coherent, just in case no sum of bets on the propositions in that set S at the corresponding odds will give you a certain loss, or gain, actually, or gain. Either loss or gain. People concentrate on loss because that impresses us more, but in fact it also works for gain. There must be a positive gain line. Anyway, failure to impose, now this is where we come to crunch. Failure to impose countable additivity leads to incoherent assignments. So here you've got a big argument for countable additivity. Without it, you're sunk, you're incoherent, people will take money off you, you'll lose your shirt, next week you'll be a pauper. Here's a simple example, a countably fair infinite lottery. This is an example discussed by Definetti himself. So suppose you've got a set of possibilities labelled by the natural numbers. And you think, as far as you're concerned, each of those numbers is equally possible. So imagine you've got some sort of screen, maybe you think God's behind all this, you've got some big screen and someone's doing something, a natural number's going to appear on the screen. Okay, you express this, so you think each of those is equally possible. You may or may not be right, but at least you should have a right to think they're equally possible. The trouble is, in that case, you'd like to say they've got the same probability. Well, of course, if you've got countable additives, you can't do that. Because there's no way you can have, if you've got a countable, not countable later, but if you've got a countable set, you can't obviously give them all the same, countable infinite set, you can't give them all the same possible probability, because they would add to a very large number. So the only way you can do it is by giving them the value of 0. So if you want to say they've got the same probability, I say accepting infinitesimal values. These things have got very popular among philosophers, and again I defer to the gentleman in the orange shirt over here, who's written a book, in fact more than one book I think, John, isn't it?
I'm afraid so.
Infinite many, isn't there? There's hyper many, I think. I'm not going to talk about infinitesimal values, for the same reason I'm not going to talk about objective chance, which is that I don't think that anyway, whatever. There's no such thing as the infinitesimal doesn't exist. It depends on the choice of what's. So there's no such thing as the infinitesimals attached to the real line, for example. They don't exist like that. So you can't really, and in a country anyway where people are now getting rid of the cent, to start talking about bits in terms of infinitesimally small numbers is sort of really pushing it. Okay, the trouble is, okay, so you want the uniform distribution, but the only way you can get that is by having probability 0, for mathematical reasons. But this distribution is easily shown to be incoherent, according to the definition that I just gave, because somebody bets a bet of $1 against each n, number n, guarantees a certain loss of $1. Because you know that those are 0 odds. Because one of those is going to come up. You're going to lose that $1. Otherwise you'll break even at 0, but on that one you'll lose $1. And one of those numbers is going to come up, so you'll end up with a net loss of $1. In fact, countable additivity, of course, guarantees that you can't do this because it doesn't allow you to have that uniform distribution in the first place, but it also is fairly easily shown that it guarantees invulnerability to incoherence in general. So you can show, there's a simple theorem that says, as long as you're countably additive, you will never be incoherent. So there's a big argument for countable additivity. One that impresses Bayesians very, very much, enormously. So this is the consensus view among Bayesians, actually, which underlies, as I said, the cheerful use of Dutch book arguments to prove that various bits of Baroque ornamentation should be added to the Bayesian theory, like the so-called reflection principle. And this view is summed up by a guy called Patrick Maher. Definetti cannot consistently reject countable additivity, and there are other people from Skirms and very many other people. They all agree you can't do it. I mean, if you want to avoid coherence, you've got to have countable additivity. But Definetti did reject countable additivity. Definetti invented this whole theory. He invented the notion of coherence, and he still said no. No, you don't. You don't have to be incoherent and finitely additive. Was this eminent mathematician and probabilist guilty of an elementary error? It seems unlikely, and indeed he wasn't. So let's see why he wasn't. So now we come away from vulgar Bayesianism to Definetti's own concept of coherence. Out of this one, but it's not just, by the way, here's what Definetti said, isn't it good, we're going to come up with some arguments against countable additivity from this discussion, because what Definetti did was to expose some of the awful things that did, if you impose countable additivity, some of the things that happen to you then, and they're not very good either. So, but hang on, we'll come to those. Anyway, let's first of all look at his concept of coherence. An agent estimates, so this agent goes around, and this agent has something called a prevision function. It evaluates all sorts of bets. You assume that this prevision values bets independently of how they're presented, simply as mappings from states to money. And you assume it's linear, that it adds over finite sums of bets. There's a unique value of the odds, which makes the provision of a bet equal to 0. So think of provision as expectation. It's expectation without the probability theory there. It's your own sort of expectation, the personal expectation. So where your provision, where the odds make the provision of that bet 0, those are your fair odds, because there's no advantage to either side. If a positive would be towards the seller of the bet, if a negative would be towards the buyer of the bet, where it's 0, it's to no one's advantage. It's evenly balanced. So they're your fair odds, and that's your personal probability. Good. Class of bets, now is supposed to be closed under finite sums. And since provision is additive, the sum of the finite number of fair bets is also a fair bet, because the sum of the finite number of zeros is 0, and 0 is the mark of being a fair bet. Okay, so fair bets are closed under finite addition. Now, so it follows that if a finite sum of fair bets, according to your valuation, can be shown to give a certain loss or gain, then you must conclude that a fair bet has given a certain loss or gain, a fair bet has given a certain loss or gain, which of course is inconsistent. I mean, you know, you're saying here's a fair bet and it gives a certain loss or a certain gain. Hence, your probability assignment has forced you into an implicit contradiction. However, your prevision will never declare any infinite sum. Now, we come back to the lottery now. Your prevision will never declare any infinite sum of fair bets fair, because it's simply not defined on infinite sums. It's only defined on finite sum. It's a linear function, so it's only defined on finite sum. So it'll never declare an infinite sum of fair bets fair. Therefore, you can be convicted of inconsistency only, or incoherence, only if there is a finite sum of bets, each of which is fair to you, and which generates a certain loss or gain. So that's the only condition which can be really incoherent. Only if there's a finite sum of bets, which would guarantee a sure loss or gain. So here's Definetti's own definition of coherence, which he also called consistency, for reasons that are apparent there. The set of betting quotients is coherent if no finite sum of bets at those odds will generate a certain loss or gain. Okay? So it's the finiteness that's important here. Now we go back to in the lottery, if you look at finite sums of bets at 0 odds, on 0 occurs, 1 occurs, n occurs, you won't get a certain loss. You can never get a certain loss. Because you can bet that any finite number won't occur, and you can be right. That number won't occur, but it may be one that outside will occur. Because you've only got a finite number at a time, you can never be forced into a sure loss if you only bet on a finite number of those things. Hence, by Definetti's own definition, uniform distribution is actually coherent. It was wrong. The vulgar view is wrong, actually. Definetti makes it abundantly clear, he discusses this at great length. Because coherence, you are incoherent only if a finite number of bets guarantees a certain loss or gain. So this is a sort of technical point about coherence. So what we conclude from this is that since only finitely many probabilities ever figure in a finite sum of bets, we can conclude that any personal probability distribution is coherent so long as every finite subset is coherent. I put consistent in, I should, because that's sort of, again, begging the question of it. It looks like something that's familiar to a logician. It looks like compactness. And it's a bit like compactness. Personal probability distribution is coherent just as long as every finite subset is coherent. I shouldn't bring this. Nowhere. So what saves? So how the sort of the Definetti theory of coherence escapes the uncountable fair lottery, and why that uncountable fair lottery is not incoherent, and it all rests on this prevision function being only adding finitely. So it rests entirely on your prevision function only adding over finite sums of bets. Because that's the only way, because only then do you count a finite sum of bets fair just when every bet in it is fair. So is there a principled reason then? Because it looks like he's getting off on a technicality here. Is there a principled reason, other than saying the countable fair lottery, is there a principled reason for not extending provisions to infinite sums, other than saving the countable fair lottery from incoherence? Well, before I discuss that, I'll come on to that next. There are two interesting results, theoretical results, both due to Definetti. One's the fundamental theorem, A coherent assignment to any set of propositions which contains the logical truth and gives it probability 1, it can be extended to any algebra at all, which includes that set of propositions. There's no limit on the size of the algebra, including algebra. It can be extended to a coherent distribution of algebra. And then there's the famous Dutch book theorem. The coherent assignments to any algebra due propositions are exactly the finitely additive probability function on that algebra. So coherence coincides with finite additivity. So far from coherence being the big boost for countable additivity, in fact, it's entirely equivalent to finite additivity. The coherent assignments to any algebra G are exactly the finitely additive distributions on G. It follows now, some further interesting things follow from this, that you can put the property 0 on every natural number, and you can then extend that 0 distribution over a natural number to a full finitely additive distribution on all the subsets of the natural numbers. And you can even do it in such a way that the set of even numbers get the probability of half. There are extensions which give the set of even numbers the probability of half. It also follows that there's a finitely additive probability on the power set of any infinite set which assigns the value 0 to every singleton member of that set. Now this isn't true for countable additivity, because there's a famous theorem of Uran that says the first uncountable ordinal, you can't do that there. It fails. And if you assume the continuum hypothesis, that means you can't do it with real numbers either, because the first uncountable ordinal then is just the cardinality of the set of real numbers. So that's very interesting. So here you've got a feature of finite additivity that looks very, very much more pleasant. Countable additivity just simply can't be extended beyond certain limits. It certainly can't in general be extended to the full power set. Finite additivity always can. Any finitely additive distribution can be extended to any including algebra whatever, including any power set. So that's an interesting result. Now we've got here, I don't know if people have recognised this, but in the countable fair lottery we have a sort of reprise of Kleiberg's lottery paradox. Now his was a finite lottery, but it was large enough to have, with a non-zero probability threshold, for accepting that events won't occur. So I accept that this won't occur as long as its probability of occurring is less than some number. So for example, a big enough lottery, I simply accept that each ticket will not be drawn. Kleiberg pointed out this is perfectly consistent. It's perfectly consistent. I mean, it's just you're doing this sort of threshold value, and it's quite consistent. You've got a sort of, it's like a type of omega, what's called omega inconsistency. I accept that each one of this infinite set, or this finite set in Kleiberg's case, won't happen, but I also accept that one of them must happen. Just omega inconsistent. When you look at finite, the natural numbers. And of course, a finite lottery with a non-zero probability threshold simulates an infinite lottery with a zero probability threshold. So in a sense, the two are the same. Kleiberg equals Definetti, up to a point. So countable additivity, to sum up, after that little excursus into the recesses of Definetti's mind, is not implicit in his theory of coherence. I said it might be objected that his theory escapes on the technicality. Countable additivity is only not implicit because the class of fair bets is closed only under finite sums. So what principle? Is there a principle that underlies this restriction? Yeah. What is it? Countable additivity forbids you, as Definetti pointed out, to express your true opinions, where these are far from being inconsistent, and may well be true. In the Definetti lottery, you're not allowed to have, with countable additivity, a uniform distribution. But what if you think there's God up there drawing random numbers? I mean, it's not impossible that God's doing this. A lot of time in his hands, I mean, why not? No, it's a symmetry. In other words, I can see possible symmetries that would underlie this uniform distribution. Why shouldn't I be allowed to say so? Well, no. So you're not allowed to. Only very biased distributions over countable partitions are permitted. On a countable partition, nearly all the probability has to be carried on a finite subset. And as n tends to infinity, so the probability left tends to 0. So it's all concentrated at the front end. But very biased. In other words, you're only allowed extremely biased. So on the real line, take an interval of real line, well, you can have a uniform. Countable additivity allows you to have uniform probabilities on the real line, constant densities. It allows you to have uniform probabilities on finite sets. But when you come to the countable case, it won't note your even though you think there might be a symmetry that justifies that distribution. Quote from Definetti: if this lack of symmetry does not reflect the actual judgment of the subject, how can we then include in the definition of consistency, in a purely formal sense, coherence, a condition which does not allow him, her, but definitely him, to assign equal values, necessarily zero, to all of the probabilities? Such limitations on the choice of the probabilities are altogether extraneous to the essence of the consistency condition. In earlier works of definition, Definetti for Kaiberg got his hands on the 1937 paper, you found that coherence, or coherence is translated as consistency, with Definity's approval. He meant consistency. There are other examples of how countable additivity imports its own bias. Here are two. Suppose I have a initial uniform distribution over a finite interval. I'm later told that the random variable can take only rational values. Well, what happens then? My updated distribution has to be highly non-uniform, because the rationals are countable. So then it has to have this very biased distribution. Although there's nothing in the information I've been given, the factual information doesn't tell me that, a supposed law of probability does. So this supposed law of probability actually imports its own bias. Another one. This is, suppose that possibility space is a set of all infinite sequences of zeros and ones. Suppose H is the hypothesis that the truth is the singleton sequence of all ones. So that H says you're always going to 1. The experiment is a sequential observation of the data emitted. Let En report that the first n observations are all 1s. So there's classical enumerative induction here. Forget the next two lines, they're not really important. Look at the last line. Countable additivity implies that countable additivity implies, for the reason given the two previous lines, but I'm sort of going a bit short, so I'm not going to answer them, that the probability of H given a uniform sample of ones of size n tends to 1 as n tends to infinity, which is remarkable. Given Hume's skeptical arguments, you shouldn't have a logic which tells you that all the information about the universe is conveyed in some finite set, especially with the complements infinite. So again, importation of content which really shouldn't be there. So this convergence is entirely an artifact of countable additivity. Under finite additivity, you can't derive it. In fact, there are finitely additive distributions such that the probability of H, given those observations, remains at the prior probability of H. So, finite additivity, very good. Allows us to be human skeptics. So, countable additivity imports bias a priori, and this clashes at a more philosophical level with one of the deepest of Definiti's beliefs, though curiously not one associated with them, despite the fact that his most famous paper is called Prevision, its logical laws, its subjective sources. Definetti actually believed that the laws of probability are laws of logic. Quite explicit about it. All these laws should do, according to him, is to enable you to deduce what's implicit in any set of probabilistic premises. Quote, as for the logic of certainty, the logic of the probable adds nothing of its own, it merely helps you to see the implications of what has gone before. As I said, just en passant, we all now talk about coherence because of Kaiberg, who was the translator of Definetti's famous 1937 paper. And here's Kaiberg's reason for using coherence. Consistency is used by some English and American authors, and it's perfectly acceptable to Definetti. So acceptable that in the footnotes that he added, he put consistency in brackets after coherence. You can just check it out in that paper. But it is ambiguous from a logician's point of view because applied to beliefs, it has another very precise and explicit meaning in formal logic. As the words are used in this translation, to say that a body of beliefs is consistent is to say, as in logic, that it contains no two beliefs that are contradictory. Well, I don't know about the two there, that shouldn't be there. There's no set of beliefs that are contradictory. Not just pairwise contradictory, yeah. So it's sort of a little mistake. To say in addition that a body of beliefs is coherent is to say that the degrees of belief satisfy certain further conditions. So here's Kaiberg saying, no, you mustn't use consistent because it has a perfect good meaning in logic that it doesn't have here. But the main claim of Definetti's paper is that incoherent property assignments are literally inconsistent. So quote again, one should clearly, so if you've got an individual who's led to declare a bet fair, which is manifestly unfair because it leads to a certain loss, or again, then, quote, one clearly should say that the evaluation of the probabilities given by this individual contains an incoherence, translated by Countably, an intrinsic contradiction. In the footnote that goes beneath the text, where you find coherence, you also find in brackets afterwards, added by Definetti in 1964, consistency. Definetti was a thoroughgoing logicist. Definetti, subjective source is logical laws. It's logicism. He's a logicist as far as probabilities is concerned. I say, if Definetti's views that the finite as the laws of probability or laws of logic can be justified, it'll be good news for Bayesianism. Since, considered under its orthodox interpretations of epistemology, it doesn't work. It's hopeless. I mean, it's talk about bad models in deductive logic, this is an awful one, because of this logical omniscience problem. I mean, how can you possibly know, somebody comes along with bits of semantic set theory and says, okay, I want to know what the probability of this is, you've got to decide whether it's logical truth or not, but before you can sign probability, you've got to decide that. It is sort of preposterous. Fortunately, however, Definetti's claim can be justified, though he did not do so himself. I'm just going to do so in the brief last 5 minutes of this. I think God was spoken here. Oh yeah, just briefly look at classical propositional logic. There's one way of doing this that's slightly unfamiliar. You develop classical propositional logic simply as, not in terms of sentences and sets of sentences, but in terms of assignments of truth values. So you can develop it as a theory of consistent estimates of truth values. And an estimate, or an assignment of these estimates, is consistent just in case it agrees with the truth values assigned by some Boolean distribution over the whole propositional language. So your assignment of truth values is consistent just in case it agrees with this full Boolean evaluation of truth values on the language. Okay? You get an entirely equivalent treatment. The connection with the ordinary notion is immediate. A set of sentences is semantically consistent in the ordinary sense, just in case the uniform assignment of one to its members is consistent in the sense above, which is good. Now, this way of characterizing propositional logic, consistency, is that it shows there's nothing specifically logical about logical consistency. If you're back to the old mathematical view of consistency as solvability of equations subject to constraints. In this case, the constraints are those laid down by a truth definition, or the Boolean clause in the truth definition. So what's so very different then? It was noted earlier that an intuitively satisfactory definition of consistency for personal probability assignments was in effect given by Definetti. They don't need you to declare a bet fair, which demonstrably isn't. And in view of the theorem that I cited by him, they don't do that, they don't need you to do this, if they are given, if and only if they are given by a finitely additive probability. So we can now define that assignment of personal probabilities could be consistent as follows. Let L be the algebra generated by any set S, let the P of S be an assignment of probabilities to S. That assignment of probabilities is consistent just in case it agrees with a finitely additive probability function on the full algebra. That's very similar to the definition for deductive propositional consistency. Very similar. Indeed. So compare. A consistent assignment of truth values to a set of sentences from a propositional language is a function from that set to the two numbers 0 and 1, which agrees with a Boolean valuation on the language. Below it, a consistent assignment of personal probabilities to a set of propositions is a function from S to, not 0 and 1, but the unit interval, which agrees with a finitely additive probability on the algebra generated by S. Aren't they similar? Even the... So from what differs here is the value space, the set 0, 1, and the interval 0, 1, and the particular nature of constraints. But then Frege defined deductive logic as what follows from the laws of truth. So it's all about the laws of truth, the general laws of truth. Propositional logic is what follows from the general laws of probability, and they are finitely additive. So we can go a bit further, call any Boolean full Boolean valuation in the deductive case. So a model in the deductive case, suppose you've got this valuation, an assignment that's consistent, means it agrees with the full valuation. The full valuation is called the model of that finite assignment. And that's not necessarily that assignment's over this set of propositions. So we use the word model for that. You use a model in exactly the same way for the propositional case. if I've got an assignment of personal probabilities that agrees with the finitely additive probability on the full algebra, that finitely additive probability on the full algebra is a model of my assignment. So now you get some salient properties of probabilistic inductive logic. Non-amplitivity, if content is measured by models excluded. This follows from that, just in case all models are this and models are that, so they both satisfy this condition. An assignment has a model just in case every finite subset has, but that's all sort of nice. And extendability. A consistent assignment to a set of sentences can be extended to any including language, just as in the propositional case, any consistent assignment of propositions can be extended to any including algebra. So you have a remarkable formal similarity. They differ only in the value set and in the specific nature of the constraints applied. Finally, Definetti again, just to round the discussion off, at which point I should stop. It is beyond doubt, says he, that probability theory can be considered as a multi-valued logic, precisely with a continuous range of values, and that this point of view is the most suitable to clarify the foundational aspects of the notion and the logic of probability. Thank you.
Thank you very much. We're open for questions. Not even the man in the orange jumper?
It's on the cat and omnibus.
Yeah, I did have some thoughts about it. You're making this analogy, which is very nice, in my opinion, what is good, between probability and logic. That analogy really forces, in some way, the attention to finitely additive measures or finitely additive charges are called. I think it is actually the adding of charge of electrical charges. I believe it came from this. I don't know, but yes, that is the term. Because of course, there are lots of constraints, very big constraints, in the logical case, right? On countably additive. Right? I mean, in general, you can show that if you simply instead of logic, just talk about measures on Boolean algebras, for example. I mean, they're very big constraints, of course, as you would know, on the existence of countably additive measures on Boolean algebras, where there are virtually no constraints on finitely additive measures. And I mean, so if you pursue this analogy between Boolean algebras and probability, then naturally the countably additive are going to fall by the wayside, since they're very special cases. And I guess that's really that's one of the underlying points.
Well, thanks for the charges. I didn't know that.
Yeah, I think that's what it is.
Yes, Bill.
I think you've done an excellent job defending Definetti's not proposing countable additivity as the fundamental constraint on what counts as rational degrees of belief. Now, some of you didn't say this, but I just want to make sure there was a sort of another lesson that some might have been gotten, and that is that in cases where people are using countably additive models to carry out certain kinds of investigations and background assumptions for doing it, there's a slight suggestion here that all of that would be somehow and I hope you're not saying that. You didn't actually say it, but I think you should come out and make it clear that doesn't follow from anything he said.
No, permissiveness is what I said.
At the beginning.
Yes. Yeah, no, permissiveness all the way. Yeah, finitely additive doesn't mean you're not allowed to have finitely additive probabilities. And in fact, in some cases, it's very natural to do. There's a very interesting book which was published after his death by the physicist E.T. James, a monumental book, and this is very much the attitude taken here. I mean, you let the problem, I mean, it sounds very vague and over-permissive, but the way he deals with it is actually very, very nice. You let the problem determine whether you are going to be countably additive on this, where it's just natural in some cases to have this sort of continuity in your model. The model itself says that it should be continuous. In other cases, it doesn't. But you let the problem decide. And there are lots of cases where so to appeal to symmetries, where the symmetry suggests that you should have some sort of continuous, some sort of countably additive approach. Yeah, no, it's purely permissive. As opposed to countably additive you can, where it's not. Where you're just not allowed to have only, because of the alleged problems, you must necessarily have countably additivity. Although Colin said in his monograph, the only real reason for this is convenience. I think there's a quote that says you get some nice results, and he proved a lot of them from countable additivity. You get some very nice results, but at the end of the day, it's elegance and something like convenience. I think that's all he said by way of justifying it.
I think that's right.
Yeah.
Rob.
You were mentioning about the radon-Nikodym derivative. How does that enter in the case of either CA or FA probabilities, and where could you sort of either use it or discard it?
Well, it enters in countably additive probability because Colin shows that this thing will fulfill lots of the properties of a countable, a conditional probability. So it will agree with any conditional probability where the conditioning event has finite probability. And it will give values where it doesn't, because it's defined simply by an integral equation. And you don't get a separate conditional probability function. It's there implicit in the absolute probability function. So without going into sort of further details, but then it has these problems associated with it, which all the authors cheerfully acknowledge, including Colin, that it doesn't make any sense to talk about the conditional probability of an isolated event of probability 0. Because it depends what limiting process you used so if it's the value of a particular random variable, what limiting process did you use to get down to that? Well, you embed it in a range in intervals of positive probability, and you shrink that interval down to 0. So you start with an ordinarily defined conditional probability, shrink that conditioning event down to a set of probability 0 to a point, and this random Nikodym derivative guarantees that you'll get something that's defined almost everywhere.
Yes, toward the back there.
I'm sorry, some concerns about the uniform sphere distribution that you raised an example to contradict the legitimacy of additivity, I believe, countable, like the Burrell's. I think the problem, the concern I have is that using spherical coordinates inherently raises the problem.
Yes.
Because you cannot use a single you can't use a single chart mapping to map a sphere.
Yes.
And so, doesn't that kind of just justify your initial intuition instead of just presenting, a possibility of, it might be a uniformly distributive space.
Yeah.
But now we're contradicting instead of saying, okay, well, I know there's an inherent problem, and here we go, look at that, there's a contradiction. And so,
yes, I think the answer is that famous universal answer, yes and no. So we're in paraconsistent logic now. The element of the sphere on the surface of the sphere is, of course, it's strange because it goes to it's long meridians, and so it goes to 0. Yeah, that's why you get the cosine for the distribution of latitude given a particular longitude.
But if it's proportional to cosine lambda, wouldn't the probability at the poles be 0?
Yes. Yeah.
But then
it's because the loom goes down to 0, and it takes that element of area, which is not a rectangle.
But it contradicts your notion that it's uniform distribution across the sphere.
No, the uniform distribution exists. So there is a uniform distribution across the sphere. I mean, it's 1 over whatever is 4 pi r squared. It's a uniform density distribution, 1 over 4 pi r squared.
Right, but then you can't mathematically kind of depict it or say that's proportional cosine lambda based on.
No, it is. You do the calculation. It is. Yes, in fact, it all comes from the same source. Yes, it is consistent. It comes from there. In fact, what you get is you get an unconditional. You get unconditional probabilities for the latitude and for the longitude, which are independent of each other. So the unconditional property of latitude is independent of unconditional. But that all comes from looking at the actual element of area and that uniform distribution. They're all consistent. I mean, they do tie together consistently. Take my word for it. That's many an hour I have looked at this, but yeah, it is just in fact. I can talk to you afterwards about it actually, but they are consistent.
We have more questions. Yes, Chris.
This is just really a follow-up to Bill's question, but just to make sure I understand that in the cases where you accept countably additive models, the point is that there's new things that are being introduced as part of the problem, which allows you to sort of be adding content that you think in the general case you don't want to do because you'd be adding. So the contrast is between thinking of this as a logicist approach to probability, or thinking of it as a sort of problem-oriented case where you're allowed to further specify the problem and then countable it might be.
But they're consistent as well because you're a logicist. You're adding in premises. You're adding in further information.
Mm-hmm.
That's all you're doing.
Okay.
Yeah. There is one sort of strange. I was going to end on this, but I ended early. One's rather sort of strange consequence of the finite additivity approach, which is that if you think of the lottery again, can I just put this up on the? Will it matter? I mean, it's just a page, but it sort of goes against me in a way, as you'll see why. The lottery strikes back. Okay, go back to the. I said you might want to appeal to the uniform distribution because you think that God might be selecting from the natural numbers. Okay, so you have two hypotheses. One is your hypothesis A, that this is what's going on, or something like it. And B, that it's a mortal doing it, and because of human limitations, you only think of the first few natural numbers. It takes you a long time to get to the end. Okay? So you have a biased distribution. You have 2 to the minus n, okay? But you think they're equally likely, these models, these hypotheses. One will, let's assume that they're mutually exclusive, and they're not necessarily the way I put it, but let's assume they're mutually exclusive, and each has a probability of a half. What you get next is rather surprising. The total probability of getting in, given that these are exclusive, either one is true or the other is true, and it doesn't matter whether they've got confidence of half, assume they've both got finite probabilities that add to 1. Well, it turns out then that the probability of A, conditional on any observation at all, is 0. Whatever number you look at, the conditional probability of A is 0. You just do the calculation, simple Bayesian calculation. And the probability of B, whatever number you look at, is 1. And you know this even before you looked at the number. So there's no point looking at the number. So you were going to do this little experiment of looking at the natural number, looking at this thing and seeing which number appears. You don't have to. Because you know that whatever happens, you're going to wind up with a conditional probability of A of 0, whatever number you see, and a conditional probability of B of 1, whatever number you see. And it's just a very simple Bayesian calculation. But let's suppose we've already done this calculation when we assign the initial probabilities of a half to A and B, because we think they're equally likely. You said, the whole point about this is you must allow your probabilities to model what you think your intuitions are. I think these models are equally likely, I give them a half. But I know that even without looking at the experiment, I'm going to give one posterior probability of 1, and the other posterior probability of 0. Isn't that strange? Definetti actually has this in the book. He passes rather quickly. And here you've got a classic case of non-conglomerability, because you've got the absolute probability of A is a half, but it's probability of A conditional on n for any n on that partition is 0. So classically, severely non-conglomerable. Oh, I didn't get to that. That's another one. So what's next? This looks like a contradiction, doesn't it? So I've done that calculation in my mind. I know that whatever I observe, I'll wind up giving probability of 1 to the hypothesis A, and probability of 0. The probability of 0 to hypothesis A, and probably 1 to B. And that's all based on this single, remember that initial uniform distribution over the lottery. Haven't I got myself into a contradiction? Yes or no? I put it to you. The answers. Would be what?
Like they would coincide with, like they would equate to each other, because if P, like if the chance of God choosing water is definite, then the probability of a mortal choosing the,
I shouldn't have done too much about God. Just regard A and B as two different incompatible generating mechanisms, so that they're properties. So they're mutually, especially mutually inconsistent hypotheses. They're not the way I gave them, which is
then could it be possible then that event B is true for all, like always true, like it's that event B is happening rather.
It's unfortunately it's the formalism itself. Once you assign those initial probabilities, the rest takes over. And Bayes' theorem tells you that you've got these. Once you've got those initial probabilities, you've got the result. That's that. And there's no getting away from it. And it doesn't rest on any sort of spooky stuff about conditioning on sets of measure zero, because in fact the absolute probability of seeing any particular number, the absolute probability is actually finite. So it's just a straightforward elementary probability calculation. So isn't that odd? I think there is an answer, which is that you don't conditionalize it. I think this is yet another argument which would bring us into further contested territory with Bayesians as to whether conditionalization is necessary or not. I think this shows you don't conditionalize. Once you conditionalize, you're sunk, because basically then you are inconsistent. But you don't conditionalize. Why should you? But that's my point. Everybody wants to sort of argue this out and some later point maybe win some money off me.
I've got a question from the internet. It's actually from someone watching the live stream.
Ah.
This is from T. Seldenfeld in Pittsburgh.
Teddy Seidenfeld.
Regarding the issue of probability logic, Definetti's coherence criterion for provisions generates provisions for a linear span, which in general will not be an algebra. It's the linear span of logic.
Yes. Yeah. Yep, I agree with it. Good.
Okay. We've got a couple of other questions if we have time for them from the internet.
Yeah.
So this one's from Eric Q. Would you be even more permissive and champion dropping the restriction to elucidation via fairer prices and allow elucidation and reasoning in terms of non-identical buying and selling prices? Why or why not?
Well, I don't know. I can't answer that on the spot. I don't know. I'd have to think about it. I honestly, it's not just getting out. I don't know. It's not something I've ever thought about. Possibly. Diamonds are a boy's best friend.
Okay. There's one additional question. So this is from Sylvia Winmakers. You say that even countable additives, additivity does not agree with the intuitions regarding sums of probabilities.
Yeah.
I agree. So shouldn't we look for a different formalization of infinite additivity of probability instead of being satisfied with FA? You can have such a principle if you allow infinitesimal values for the probability function.
Yeah, but the trouble with this is something I didn't really want to talk about a great deal, because there are no such thing. They're infinitesimals. They're a fiction. I mean, there are lots of. For every class of infinitesimal, there's a non-principal ultra filter over natural numbers, and each choice gives you a different set of infinitesimals, and they're not even order isomorphic. So there's no absoluteness to them at all. They're used to generate because they're a conservative extension. They're used because they're nice ways of proving classical results. But to endow them with independent existence, I think is just wrong. I mean, I don't think they have it in the way that reals have it, because they're not absolute. I mean, they're not absolute in any sense. And the other thing is that, as I said, it destroys the underlying model, because the model of coherence does depend on evaluations. You've got this prevision function. You're looking at bets. You're looking at contracts in general, which depend on some uncertain event, and you're evaluating these in monetary terms for small monetary values. And it just doesn't make any sense to start saying, well, I'm going to evaluate this as an infinitesimal amount of a dollar. I mean, it's senseless. So it just destroys the model. Yeah.
Bill,
say that there are cases where allowing for first you can have, I'll put it, controlled infinitesimals. If you take, in fact, if you think of taking conditional preference as sort of fundamental, then you can have the conditional probabilities perfectly well defined, even when the probability of the, say, the conditional probability of B on A is perfectly well defined, even when the probability of A is as close as you want to 0. And there's lots of work that was done in economics a few years ago using this stuff in game theory, where it was getting very informative results. And I don't think you can just ban the whole thing.
No.
And it would be just as bad as what you're accusing.
No, I wouldn't dream of banning it. I think, you know, it was in its use, as far as I defer to John, who knows much more about this than I do, but you do as well by the sound of it. These things generate, these things give you different sorts of proofs of classical real value, complex value results. And they don't have an independent existence. All right, you can say there are infinitesimals, but I mean, there's no absolute sense to what an infinitesimal is.
First, there are lots and lots of different sorts and ways of talking about infinitesimals that aren't. But what I want to, for one of the things that could be quite useful in a Bayesian framework is distinguishing between things that an agent treats as conceptual commitments, is that he takes as meaning postulates. If you can perfectly well take conditional probability as primitive and have and then the model that corresponds to that. I think it's somewhat unfortunate, but it's a Popper function.
Yes, I know.
And you can perfectly well generate those things. One nice thing about it is you can distinguish for an agent between taking something as a conceptual commitment and merely as a knowledge claim, and it allows you more resources for representing different kinds of acceptance and commitments that people have. And some of these seem to be like commitments that real people have, for instance, when mathematicians are doing proofs of various sorts in the way they consider some of the assumptions. And so it isn't, I don't think you should anymore exclude it because you can't find some fundamental underlying notion in that can play the role that would compete with the reals. That's beside the point for the uses of them for modeling these sorts of things.
Well, I think that, you know, having argued for permissiveness myself, I mean, I have to agree with you. It's just that I thought at the end of the day that the point was to get back from the infinitesimals and get back into a real structure by taking standard parts and things like that. Now, well, okay, but I mean...
That's not the only thing you can do.
No, all right, okay. But as far as the lottery is concerned, I defy anybody to say that it makes... Yeah, I don't think that's not... Well, but, you know, that's lots of big papers coming out of people, you know. You've got you know, you can assign infinitesimals to the lottery. You can actually add them all to 1 because they're hyper, whatever, you know, hyper countably additive, and they add to 1. So there are all sorts of, well, you know, let 1,000 flowers bloom. I mean, I don't mind. See what happens. Yes, so I'm happy to say I agree with you. Yeah, let's shake one.
Any last questions? Well, just so that you'll never ever forget us, we have a mug for you. We'll have to keep it until you die. And we'd like so thank you for
all the snow around.
Thank you very much.
Okay, thanks.